A great pleasure to introduce Professor Martin Herer from Imperial College and the École Polytechnique Fédérale de Lausanne. Martin has a PhD from the University of Geneva under the supervision of Jean-Pierre Ekman, and prior to that had positions at Warwick and NYU. He's a Knight Commander of the British Empire, so Sir Martin, Fellow of the Royal Society, and also a recipient of many awards, including the 2021 Breakthrough Prize in Mathematics, and of course the 2014 Fields Medal. And I don't have any personal anecdote with Martin, except for having beer with him at the Sin and Redemption after his Fields Medal Symposium lecture in 2017, which is of course one of the perks of being at the Fields Institute, of great relevance for me, but of no significance to anybody else. So I'm looking forward to a second memorable event with Martin. Thank
you. Okay, thanks a lot. Thanks a lot for the very kind introduction, and thanks to, and Deirdre for organizing this event. So what I want to talk about today, so it's based on joint work with with my former postdoc, Tommaso Rosati, who's now at Warwick, and some with my current PhD student, Wenhao Zhao, at EPFL. But because that's, the specific result I want to talk about is basically just an excuse to give you a bit more of an overview. And so I should, start by, okay, what is this about? So the motivation, so what is, okay, the title of the talk, so it's about singular stochastic PDEs. Why are they interesting? So what makes them singular is that they're going to be, there's going to be noise terms, so this is a sort of somewhat probability talk, even though it's going to be much more analytical. And the noise is very rough, and so that makes the solutions very rough as well, and that kind of makes them singular, right? But why are they interesting? I guess there's two motivations. So motivations like in Greg's talk, they come from physics. And there's motivation on the one hand from statistical mechanics, and on the other hand from quantum field theory. And in both cases, what you really want to do is you have some energy functional, right? So you have some space of fields, whatever, phi, and you have some energy functional or action functional, depending on whether you're in the statistical physics or the QFT side, S of phi. And the kind of thing that you can think of, the simplest one would be like the H1 norm square, right? Integral gradient phi square. So that's the canonical example, and almost everything else is sort of perturbations of that or variants on that theme. And then, right, so this should be something like integral gradient phi square plus stuff. And the interesting case is when stuff is not quadratic. And what you then really want to do is you want to sort of build the measure mu of d phi, which would be something proportional to e to the minus s of phi d phi, right? Where something like a Gibbs measure in statistical physics, where this would be Lebesgue measure, and this is sort of the density with respect to Lebesgue measure. And obviously there's no Lebesgue measure on the space of fields. And even if there was a Lebesgue measure on the space of fields, the fields in question certainly wouldn't have finite H1 norm. And so this wouldn't have any meaning anyway. And so what you do is you do, your favorite way of approximating this, right? And then what you really want to show is not just that your favorite approximation is a limit, but also that things are sort of canonical. That, if maybe my favorite approximation is different from your favorite approximation, but we should actually agree on what this guy means, right? So that's the kind of thing you want to prove. And so there's various ways of doing this. And so this goes back basically to the 60s and 70s, I guess. So one of the first non-trivial construction was actually by your supervisor, right, at Nelson, who constructed this. The simplest non-trivial case is the one where here you put a phi to the 4, and you're in spatial dimension 2, which is somehow the lowest non-trivial dimension. And then Nelson, I think in 64 or something like that, or at least sometime in the 60s, we kind of built that measure in this particular case. And there was a lot of development on that particular model around that time. So the other interesting action functionals, I'm going to talk about other interesting action functionals later. So the technique for building this measure that I'm interested in is something that was originally proposed actually by Parisi and Wu in the 80s. And what he was saying is that, well, you can look at some kind of PDE or stochastic PDE, so basically a noisy gradient flow, right? So you think of phi, you can look at the PDE time derivative of phi is minus gradient S of phi. So that gives you trying to kind of find the minima of this energy or action functional, but then you add noise to it. So that gives you some random process. And if you add the noise in a way that's compatible with, right, if you take a gradient, the gradient is always with respect to some metric. And you take the noise, which has covariance, that's like the inverse metric, so it has to be compatible with your notion of gradient. Then, at least formally, say if you're in Rn instead of a space of fields, then you get a stochastic process, which is such that you can start with any initial data, you run it for long enough, the law at any fixed time t converges to that measure, okay? So that's true on, if phi were finite dimensional, that would be true. If S is smooth enough and sort of grows enough in all directions and stuff like that. Right, and so you want to do that. So the idea is you write down formally sort of the stochastic PDE, which you guess should have this measure as its invariant measure. And then you make sense of the PDE, you show that it has an invariant measure, and then that's your construction. Okay? And in the cases where you want maybe a reality check, right? The reality check would be take a case where you already had a construction previously and prove that the two constructions give you the same thing. And then you're pretty confident that in the cases where you didn't have a construction before, what you did is sort of reasonable, right? So that's kind of the idea. And so, for example, if you do this for this example here, right, what's the gradient flow that goes with this? So that would be the kind of phi4 gradient flow. You would get dt phi Laplacian phi, right? So that's, say, if I take the L2 metric, that's the metric for my gradient. If I take the L2 functional derivative of that guy, it's just Laplacian phi, or maybe 2 Laplacian phi, whatever, put a half in front. And then the phi4 term gives you a cube here. And then you have to put noise, so I call it psi. And the covariance of that guy, right? So you think of this as being something that depends on t and x, is delta function in t and delta function in x. And so why should it be delta function in x? It's because, so what does this really mean? It really means, this is a random distribution. You test your random distribution against the test function phi and against some other test function psi. And then this is really an integral of phi of xt, psi of xt, dx dt, which you should think of phi of xt, psi of ys, delta of t minus s, delta of x minus y, and so on, right? So that's sort of the rigorous way of writing this. And now here you see that's just the L2 scalar product. And that L2 is sort of the same L2 as the L2 gradient at which, right? So it's in that sense that the noise is compatible with the gradient that you've chosen to derive the deterministic part of your PDE. Okay? Yes. Well, so here you can do that. You can do that on a lattice, right? And then you would get exactly the same equation, and you just get a discrete Laplacian here. And here you would just get like IID white noises on every lattice point, right? Of course, that's how you would want, right? Like if you want to prove, so by now there is a proof of this fact, which is that, in the 70s, people have, so after Nelson constructed that guy in 2D, there's the works by Glim, Jaffe, and Federer, and so on. We constructed that guy in 3 dimensions. And so if you want to, you can give a meaning to the solution of this equation in 2 and 3 dimensions, and you can prove that it actually has the invariant measure they constructed at the time, the measure they constructed at the time as its invariant measure. And the way you would prove that is precisely like this, right? So you do it on a lattice and you sort of pass to the limit. And yeah. Now, so another interesting example is Young-Mills. Right? And I'm not going to write down the equation. It has a vaguely similar structure. So the structure of the equation. So here now your field is not scalar, but you should think of the A as being a 1 form, and it's not a normal one. So a normal 1 form takes a tangent vector, spits out the number. That one takes a tangent vector and spits out an element of the Lie algebra of some compact Lie group that you fixed in advance. But then the equation is something somewhat similar in the sense that there's a quadratic term, which is so a bilinear term which depends on the first derivatives of A, and there's a trilinear term which depends just on A itself, and then you would add white noise. Okay, so the structure of the equation is this, and the exact meaning of these products, is the thing that defines Young-Mills. That one has additional complications, which is the Young-Mills equation has a large symmetry group, and so it's in some sense much less obvious that this measure would have any sort of meaning. And so one thing that we've done, so in the case of Young-Mills, in 2 dimensions, again, people had constructed that measure. But the way they did it for Young-Mills is that it has some sort of integrability property in 2 dimensions, so you can just guess everything. Like there's explicit formulas for everything, right? And you don't have it in 3 dimensions. Okay? So in 3 dimensions, there's basically no construction, although there are results by Ballermann that sort of go in that direction, but there's no actual construction of a probability measure that is any viable candidate for the Young-Mills measure. And so one recent result we had is we actually constructed this process. We gave a meaning to this equation, to solutions to this equation. And then what's missing for the construction of the Young-Mills measure in 3 dimensions, which is still an open problem, we haven't solved that, is that the solutions we construct are just local in time. Okay? So we know that for some class of initial data, you get a local solution. There's some well-posedness result. Everything indicates that it's the right process in the sense that in 2 dimensions, one can actually prove that it has the existing Young-Mills measure as its invariant measure. That's a recent result by Harshen and Ilya Shevirev. And in 3 dimensions, it satisfies a form of gauge invariance, which is sort of this symmetry property of the Young-Mills equations that I mentioned. So there's lots of indications that tell you that it's sort of the right object. But if you don't know that it has global solutions in time, that it might somehow just blow up in finite time, and that it tells you nothing. Okay? And so you want some kind of techniques that give you control that's global in time. Okay? And so that's what I wanted to talk about today. And the problem here, right? So in principle, you think, well, these are just parabolic PDEs, right? I mean, parabolic PDEs are sort of the simplest type of PDEs that you can possibly imagine. You know everything about them. The problem here is that the noise is very singular, right? Because of these delta functions. So the delta functions sort of show up in the covariance of the noise. So in some sense, it has the regularity of like a square root of a delta function, but in space-time, which is still pretty irregular. And so in particular solutions, for example, in this case, as soon as you're in dimension 2 or more, solutions aren't function valued. So it's not clear what that cube means. And well, the same here. And so it's even less clear what that guy means. So it's not like in Navier-Stokes, for example, has this sort of structure. But in the case of Navier-Stokes, you can put the derivative outside. You can write it as like a divergence of U tensor U. Here you cannot, actually. Okay. So just being function valued wouldn't even be enough to give a meaning to that equation. Okay, so that's sort of the problem, and that's why already to just give a meaning to these equations, you need to work, right? So by now, we have a very kind of general theory that gives you meaning to these kind of equations and tells you that, you know, you regularize it in pretty much any way you want. You add suitable counter terms that actually have diverging constant in front of them. And then you can pass to the limit and you get a finite limit, and the limit doesn't really depend on how you regularize things and so on. Okay, so we have a pretty good solution theory for these type of equations. But it's very delicate, right? So it relies on kind of approximations, taking limits, adding diverging counter terms to them, right? And so now you want to get some kind of a priori control. You cannot just out of the box just apply the standard techniques, right? So what's the standard techniques to get a priori control? Right? So for parabolic PDEs, so well, maybe the simplest technique is the one if the right-hand side were globally Lipschitz. Okay, then sure you can somehow just do your Picard iteration. You have a fixed time horizon over which the Picard iteration converges, which doesn't depend on the initial data, and then you can just iterate it, right? So that's sort of if you have global Lipschitz continuity. That, of course, here usually doesn't work because you tend to have like polynomial type nonlinearities, and they are not globally Lipschitz. The other sort of technique that you have is, which is much more promising, is if you have something like a gradient flow, right? You have a gradient flow, or even better, if you have some sort of contracting, or if you want, that's like a gradient flow for a convex functional, right? Then you know that, well, if you take any ODE, which is x dot equal minus gradient v of x, if you look at the time derivative of v of x itself, well, then you get minus gradient v of x squared, which is always negative. And so you have an a priori control, which is v. You know that v always decreases, right? So that's sort of promising because we derive these equations by starting from a gradient flow and then adding some noise, right? So the problem, of course, is that these action functionals, so the thing of which we took the gradient, is not going to be finite for the solutions to any of these equations, right? So I already told you that for phi4, the interesting dimensions are 2 and 3. The solutions are not even function valued. So they're certainly not in H1, right? They're not even in L2. So you're kind of pretty far off from that, right? And so you can't just try to find what's the time derivative of your action functional, right? Then the other kind of technique that you have is things like maximum principle. So maximum principle or maybe more generally, sort of like geometry. I mean, we've heard in Tobias Kolding's talk yesterday, right? I mean, like in the mean curvature flow, things don't cross. So that's like a form of maximum principle. And so in scalar equations, you often, like in the first one, you can expect to have some form of maximum principle. Like if you have some sort of super solution, sub-solutions, then the real solution gets squashed in between. So then maybe that can be helpful. And the final thing is if you have something like conservation laws. Right? So that's sort of, so the example for that would be, for example, Navier-Stokes. Right? So if you take Navier-Stokes, then the equation there is, well, you have this Leray projector and you have U grad U. And say if you take the stochastic Navier-Stokes and you add some random force into this, then the Navier-Stokes nonlinearity, you know that, you know, it doesn't push you inwards. Right? But if you look at the energy of your velocity field, so if you apply, say if you forget about the noise, if you take deterministic Navier-Stokes, you do the time derivative of the L2 norm square, which is the energy of your velocity field, this term just drops out, right? And then you have the Laplacian, which gives you something that decays. Right? So that's typically the kind of tools that you have in the deterministic case, at least. Right? And so ideally, right, our motivation is we would like to have a priori bounds for Young-Mills. So for phi-4, there's been quite a lot of work so in the last 6-7 years. And so in particular, it started off with a paper by Weber and Murat. And then there's a whole series of papers. There's a more recent one by Chandra, Weber, and I don't remember the third. So there was a PhD student of Hendrik as well on the paper. And there are several other papers. So by now we have very good control of the solutions to this equation. But that's the one which has the best properties you can think of in terms of global bounds, say if it weren't noisy. So if this guy weren't noisy, then this equation here, you can start with any initial data, say any function valued initial data at all, and you have a bound on the solution at time 1, which is completely independent of the initial data, right? So it's like if you take x dot equal minus x cubed on R, right? So the solution to that ODE, it reaches 1 in time 1 wherever you start from. So that one has the same kind of property, and so you have extremely good control on the solutions. So in particular, there's sort of so good control on the solutions that you can use that to get, for example, tail bounds on this phi-4 measure that are much better than what people had obtained back in the 70s. So you can get better than Gaussian tail bounds, things like that. So in the case of Young-Mills, well, first, in terms of structure, it looks a bit more like Navier-Stokes, but at least that term looks more like Navier-Stokes. This term looks a little bit like that, but it doesn't, it pushes inwards, but in some sense, it doesn't push inwards in all directions. And that's due to this large symmetry group, again, in Young-Mills. And so right now, we have basically no result. The only result that we have that gives global bounds for Young-Mills is in 2D, but that's cheating in some sense, because there we have the guess of what the invariant measure should be. You can basically prove that it is invariant, and once you know that it has an invariant measure, well, then the solutions have to be global. Because it sounds a little bit like a circular argument that you can make that rigorous. Yeah. So in 2D, you can get global solutions, but it's not because you can actually bound solutions to the PDEs, just because you know what the invariant measure is. Yeah, Robert. No, I mean, No. These dots, it just means arbitrary trilinear form. There's a trilinear thing, and it has the correct sign. But it's just that it has like Lie brackets in it, and you can have things where the Lie bracket is 0, and so that gives you directions in which it doesn't push it. So yeah. Okay. And so for Young-Mills phonemons, we have no technique. And so the result that we have is for Navier-Stokes. So in this case, we think of Navier-Stokes in some sense as a toy model for these kind of, for Young-Mills, which is the equation we're really interested in. Of course, Navier-Stokes is super interesting by itself as a model. It's maybe not that, if you view Navier-Stokes as an equation of fluid dynamics, then putting here things like space-time white noise is not necessarily a very natural thing to do, okay? So the motivation for looking at Navier-Stokes with something like space-time white noise or very irregular noise is just to, develop tools to get a priori bounds for solutions to very singular parabolic equations, okay? So now, okay, so maybe we don't have a lot of time. So let me first actually state the result that we have, but it's not really super important what the precise result is. But basically the result, I'm not even going to write it down. The result is that and all of these are in finite volume, right? So you take Navier-Stokes in 2 dimensions on the 2-dimensional torus, so we don't worry about boundary conditions and stuff like that, okay? So the easiest case that you can think of. And you take noise here, which is either exactly space-time white noise. In the case of exactly space-time white noise, Navier-Stokes is sort of special. So again, you know what the invariant measure is, so you could get global solutions by cheating. And so we take a noise which is the regularity of space-time white noise, but it's not exactly space-time white noise, and so we don't know what the invariant measure is. Okay, so we're not allowed to use this, or even in a hidden way in our proof. But basically, you should think of this as space-time white noise again. And then, on the one hand, in the result with Tommaso, we show that you have global solutions in time, but with really bad a priori bounds. So we have some kind of pathwise a priori bound, but it goes like e to the e to the t, or actually even e to the something that's t times somehow the size of the noise over the interval 0t or something like that. So it grows like really crazy fast. And then in the result with when how, we need to put a small parameter in front of the noise, or at least we don't need the noise itself to be small, but we need to be able to decompose it into something small that has the regularity of space-time white noise, plus possibly something large, which has better regularity. Okay. So in some sense, the irregular part should be small enough. Okay. And then we have a result that if alpha is small enough, you have not just global solutions in time, but you have uniform in time bounds. Okay. For alpha small enough. And so in particular, you have an invariant measure, and you even get tail bounds on the invariant measures that go maybe like exponential of square root of some normal view or something. On the solution, right? So you take this, you want a bound, so you have a bound of the form, basically expectation of u of t, smaller than some constant t. Right? And of course, it depends on the initial data as well. Actually, what we can show there is that you have some kind of Lyapunov function. So you have some norm here that's sort of crafted in the right way, so that if you take something like this, you have a bound which goes like constant times e to the minus constant t times the same sort of norm for u of 0, and then plus another constant. You have that kind of bound. Right, so that have to be distributional norms. Yeah. Yeah. So this is indeed, so the solution is just about not functional. And actually, the solution here for any fixed time, it looks exactly like if you didn't have the nonlinearity, to just take heat equation plus space-time white noise, at any fixed time, the solution looks exactly like the Gaussian free field that Greg just talked about in his previous lecture, which in 2 dimensions is just about not a function. And then in 3 dimensions, so that every time you go up 1 in dimension, you lose 1/2 in terms of regularity. So it becomes kind of worse and worse. Okay, so that's the result that we have. And so maybe let me just do a small aside on, so again, we have basically, we use in Navier-Stokes, we have this conservation law, and we want to kind of use that. And so let me just make a small aside on scalings for this PDEs, right? So say you take any kind of norm on functions or distributions on the torus, okay? And for most norms, you would have some kind of scaling exponents that's associated to it, which is you say that a norm has scaling exponent alpha if when you take the norm of u of lambda dot, and that's bounded by the norm of u times lambda to the alpha. Because here I'm sort of cheating because you can't rescale the torus in the torus, but okay, forget about that. Think of it as being on the whole space, for example, and think of it as being lambda small. And so, of course, it means you look at small scales, and with small scales, you don't really see the fact that the torus is bounded anyway. Okay, so that's what it means for a norm to have scaling exponent alpha, right? So the L infinity norm, scaling exponent 0, because you rescale everything, then infinity norm doesn't change. L1 norm would have scaling exponent minus dimension your space, right? If you rescale by lambda, you sort of zoom in, that means that you sort of stretch your function out, then the integral is going to actually become bigger by, well, in your change of variables, you get a lambda to the minus d, right? So in general, the LP norm gives you a scaling exponent, which is like minus d over p. And so one thing that it's kind of nice if you want to sort of depict this, most norms have somehow some integrability exponent and some regularity exponent, right? So the integrability exponent is like the p in the LP norm, and the regularity exponent is like the alpha in the C alpha norms, okay? So typically a norm tells you that there's so and so many derivatives that are in some LP. And then maybe there's like additional exponent that give you kind of finer control and stuff like that, right? But typically, by and large, once you have these 2 exponents, that gives you a pretty good handle on what your norm does. And so if I call, say, S the regularity exponent and P, but I put a 1 over P here, okay? Then, so 0, so here I would have the LP spaces. And the way these scaling exponents go is that they are constant on sort of lines like that that have slope dimension of your space, right? So that's what you, and the sort of Sobolev embeddings and so on, they tell you that if you have control over some norm here, then you have control over all the norms that are below a thing like that, that kind of follows the scaling slope in one direction and sort of is flat in the other direction. Okay, that's what the sort of typical inclusions sort of tell you. And then if you take any of these kind of parabolic PDEs, if you look at the nonlinearity, you can ask yourself for which kind of norms is the nonlinearity of about the same strength as the linear part at small scales, okay? And that's very easy to guess because the way you do it, you say, well, if A is in some space that has scaling exponent alpha, then the Laplacian of A has exponent alpha minus 2. And then the derivative of A is alpha minus 1. And if I multiply by a, well, basically, at least in the low regularities, these exponents actually tend to sort of add up when you multiply. So this balances out if alpha minus 2 is equal to 2 alpha minus 1. So alpha minus 2 equal to 2 alpha minus 1. So that gives you alpha equal minus 1. Okay, so it's the same for Navier-Stokes because that's sort of the same in terms of these power countings, that's the same in terms of nonlinearity. And it turns out that even for the phi-4, it's actually the same, but it's not the same equation, right? So it's now alpha minus 2 is equal to 3 alpha, but that happens to also give you minus 1, okay? Which is a bit of a coincidence. Maybe not so much because both terms show up and they really have the same strength in Young-Mills. Okay, so here is, what does this tell you? So it tells you that if you take the line that starts here, this line at exponent minus 1, then basically if you take an initial data, so forget about the noise still, so still completely deterministic. If you take an initial data that lies below here, which has sort of worse scaling exponent, then you cannot close the Picard iteration. Whereas if you take initial data that lies above that line, you can close the Picard iteration. And if you're on the line, then it sort of depends on details, right? So in most cases, what you can show is that somewhere on the critical line here, well, stuff above somewhere work and stuff below maybe doesn't work. So typically, this is sort of like the worst space, the largest space with the scaling exponent. And typically you can show, so for example, for Navier-Stokes, there's a result by Albert Koch from, I don't know, maybe 10 years ago or something, that shows that in that critical space here, the Navier-Stokes is really, you cannot solve Navier-Stokes in the sense that, smooth functions are dense in that space and the solution map just doesn't extend continuously to the space. And in fact, it becomes arbitrarily big in arbitrarily small neighborhoods of the origin. Right? So it really badly doesn't extend to the space. So that's called like norm inflation. And you can show the same thing for like phi-4. In fact, in the case of phi-4, things already go slightly wrong a bit above, like at minus 2/3 here. There's a little regime here in which you end up having problems because not just because of scaling, but at some point because of integrability of the right-hand side here. Okay, so it's not universally true that if you're above that line, you have a solution theory. If you're below, you don't. But it is sort of universally true that if you're above the line, even if you're kind of in this bad region, you put a little bit of extra conditions or something, and you do actually have a solution theory. Or maybe like for generic random initial data, that sort of regularity, you would have a solution theory or these kind of things, right? So it's still somehow much better behaved than if you're below the line. And so now if you have a conservation law, right? So conservation law typically has itself some kind of scaling exponent. So like L2 norm from Navier-Stokes. So that gives you a point somewhere on that diagram. Right? So the L2 norm for Navier-Stokes is here. In the case of Young-Mills, you have this energy functional that sort of decreases. That's more like an H1 norm, which is a bit better, right? So that's somewhere above here. And in the case of Navier-Stokes in 2D, you also have the H1 norm. So it turns out that in 2D Navier-Stokes, both the L2 norm and the H1 norm of the velocity field are preserved. So you actually have two conservation laws, so like both of these points. And now whether conservation law is useful or not basically depends on whether that point lies below or above the critical line, right? Because if it lies above the critical line, you have some kind of a priori bound that tells you that thing is going to be finite. And if you know that it's finite, you can extend your solution further, but use Picard iterations and everything goes fine. If it's below that critical line, then you're in trouble, right? So that's why Navier-Stokes 3D is still $1 million problem to get global well positiveness, because if you do in dimension 3, you take the line of slope 3, right? That starts at -1 here, but at 0, it's at a third. But the conservation law you have is the L2 norm, which is at a half here, okay? And so it's below the line. That's why it's sort of useless to get you global web positiveness results, okay? And in the case of 2D Navier-Stokes, on the one hand, you're sort of just borderline, because if you take the slope, the line of slope 2, right, then it intersects here exactly at a half, which is the L2 norm. But in principle, for the deterministic theory, that's much better because you have the H1 norm as well. And so that's why Navier-Stokes 2D is considered sort of super easy. It's because you have this other conservation law, right? So if you didn't have that, it would be okay, but it would be kind of critical, right, in 2D. And so now what happens when you add this noise? So when you add the noise, it tells you that whatever you do, your solution is not going to be better in terms of regularity than the solution to the heat equation plus noise, right? And that one, so what's the regularity of that? Well, basically in dimension 2, it's sort of 0. In dimension 3, it's -0.5 and so on, right? So it's what I mentioned before. And that somehow doesn't, that's something which is very homogeneous in space because the white noise, everything's translation invariant and it's random. So the integrability exponent doesn't really play any role in terms of what space you belong to. And so that means that you have a line here, which is a horizontal line, which is somewhere near 0. And your solution is not, whatever you do, it's not going to be better in terms of regularity than that. So you're always going to be below that green line in terms of regularity, right? So now basically all these equations in dimensions less than 4 are such that at least the green line is above this point here, right? If you're dimension 3, the green line would be at -0.5. It's still above this. But the problem is now your conservation laws become, like this conservation law becomes really kind of useless, right? Because it's way above that green line. So you have essentially no chance of being able to use that because the regularity of your solution is going to be way too low to use that, right? This one is sort of borderline, right? So that's why in some sense, this Navier-Stokes 2D with the space-time white noise is kind of interesting because this all sort of crosses at the same point, right? And so that's why we can sort of deal with it, but just about, right? It's because we can only just about make use of the L2 conservation law, even though solutions are not in L2. But we really cannot use the H1 conservation law at all. Okay, so I meant to, okay. So I meant to show you an actual calculation to see, how one actually deals with that. But I have sort of -2 minutes, so maybe just give you a very quick idea. Sort of like the general idea is always try to somehow decompose your solution into some small high-frequency bit that you have pretty good control over because it's mostly determined by what the noise does and not so much about what the nonlinearity does. And then a remaining bit, which is kind of large but smoother, okay? And then the hope is that you can write things in such a way that you can get something which is close to like an effective evolution on what happens on the larger scales. Okay, so it's really sort of in the spirit, if you want, of Wilson's renormalization group, where you say, well, you have these physical systems where you have stuff going on at very small scales, which appears to be very singular when you look at what happens at large scales. And so you should really sort of look at a whole bunch of kind of effective equations at every scale that are sort of compatible with each other, right? And you should, at the end of the day, look at only sort of analyze the effective dynamic at scales of order 1, which you're really kind of interested in, okay? So you're essentially trying to do that. So you can't quite implement Wilson's RG in a way that's useful here, but still, at least you can use that as a sort of guiding principle to figure out what's going on. And then, yeah, I think that maybe I don't think I have time to say more than that. Okay, thank you very much.